Hello everybody, this is Sridevi, Associate Professor of ECE Department, BVC Engineering College, Odalrevu. I welcome you all to the subject electromagnetic waves and transmission lines. In this video, I am going to discuss about reflection and refraction of a plane waves at media interface. As we have some basic knowledge on uniform plane waves propagation in unbounded homogeneous isotropic media. Now, let us try to explore how plane waves will behave at a media interface. When the plane wave traveling from one medium to the another medium, it is partially transmitted and partially reflected. When a plane wave reflects from media interface, the strength of the reflected wave is always less than the incident wave. The parameters conductivity, permittivity, and permeability of the two media determine the amount of reflected wave and the transmitted wave. Here, the ratio of reflected wave and the incident wave is known as reflection coefficient. And the ratio of transmitted wave and the incident wave is known as transmission coefficient. To obtain the values of reflection coefficient and transmission coefficient, first of all we have to write the expressions for electric and magnetic fields for the two media and apply the boundary conditions at the media interface. So we are going to obtain the values of unknown coefficients. Here we will discuss two cases of plane wave reflection, one at normal instance and other at oblique instance. In normal instance, the direction of the propagation of the plane wave is normal to the boundary between two media. And in oblique instance, the direction of propagation of the wave is arbitrary. So here we are going to consider the two media as a lossy conducting medium or a perfect conductor or lossless medium. Here in the oblique instance, we are going to study about the effect of polarization of a plane wave, Brewster angle and total internal reflection. So this oblique instance is discussed in the next section. First, let us see the first case, that is normal instance. So let me consider a case 1, that is reflection of plane waves from dielectric media interface at normal instance. So here we assume that the incident plane wave is normal to the boundary between the two media. That is, we are going to consider a plane wave propagating along positive x direction from medium 1 to medium 2. Let the medium 1 lies in x less than 0 region characterized by the parameters conductivity, permittivity and permeability, which are denoted as sigma 1, epsilon 1 and mu 1. And the medium 2 lies in the x greater than 0 plane characterized by sigma 2, epsilon 2 and mu 2. And now let the wave is incident normally onto the boundary at x equal to 0 between medium 1 and medium 2 as shown in the figure. We will see the figure in the next slide. And see, look at this diagram. Here, this is the boundary or media interface which separates both the medium 1 and medium 2. So this boundary surface is taken at x equal to 0. That is, it is a YZ plane. It lies in the YZ plane. X less than 0 region is denoted by medium 1 with a parameters conductivity sigma 1, permittivity epsilon 1, permeability mu 1. And the medium 2 is characterized by sigma 2, epsilon 2 mu 2. We look at these parameters zeta 1 and zeta 2 later. Now let me consider, as I told you before, the wave is incident normal to the interface along x direction, positive x direction. So you can observe here, some part of the wave is partially transmitted and some part of the wave is reflected back into the medium 1. Here the subscript I, R and T you can see here. These are denoted for incident wave, reflected wave and transmitted wave. So here the electric field vector and the magnetic field vector of a plane wave are oriented in such a way that when the wave propagation is along positive x direction, the orientation of the electric field vector is assumed to be along positive y direction and the magnetic field vector will be along positive z direction. So here the z direction is pointing outward of the plane, that is perpendicular to this plane. And ER and HR are the reflected field strengths of the reflected wave. ET and HT are the field strength of the transmitted wave. Here, when the wave is reflected back into the medium 1, the direction of the reflected wave is in the opposite direction of the incident wave. That is, the orientation of the electric field vector does not change, but the orientation of the magnetic field vector is changed in the negative z direction. That is, it points it. The vector field is pointed into the plane, that is along negative x direction. And here in the transmitted wave, there is no change in the direction of the field vectors. So here, as I told you, when the wave is incident normally, some part of the wave is transmitted into the medium 2 and some part is reflected back into the medium 1. So this depends on the wave impedance of medium 1 and medium 2, which is denoted by eta 1 and eta 2, where this gives the relationship between electric field and magnetic fields of the waves. Here, note that for the normal instance, we assume that the polarization of the incident, reflected and transmitted waves are same and satisfy boundary conditions. Here I am assuming that the incident wave, reflected wave and transmitted waves are linearly polarized. And the electric field strength and the magnetic field strength is related as E is equal to eta into H, where eta is the wave impedance of the medium. So from the diagram or from the geometry of the figure, the incident electric field is equal to eta 1 into incident magnetic field. This is the electric field intensity of the incident wave in medium 1. And electric field intensity of the reflected wave in medium 1 is given as ER is equal to minus eta 1 into HR. This minus sign indicates, as I told you, the reflected wave is in the opposite direction of the incident wave. So we get a minus sign here. And the electric field of the transmitted wave in the medium 2 is related as ET is equal to eta 2 into HT, where eta 1 and eta 2 are the wave impedance of medium 1 and medium 2 respectively. Now the total electric field and magnetic fields for medium 1 are given by the total electric field of the medium 1, E1 is equal to EI plus ER, that is the field strength of the incident wave plus field strength of the reflected wave. And the magnetic field strength in the medium 1 is equal to, the total magnetic field strength is equal to HI plus HR. So the total electric field and magnetic field for medium 2 are given by E2 is equal to ET and H2 is equal to HT. Now from the boundary conditions, the tangential components of the electric and magnetic field must be continuous at the boundary or at the media interface. That is, the tangential component of the electric field intensity in medium 1 should be equal to the tangential component of the tangential electric field component of the medium 2. And similarly, the tangential components of the magnetic fields from medium 1 is equal to medium 2 according to the boundary conditions. So therefore, at x equal to 0, the tangential electric field components for the medium 1 will be EI plus ER, and for the medium 2 it is ET. So EI plus ER will be equal to ET. Similarly, the tangential component of the magnetic field for medium 1 is HI plus HR, which is equal to tangential component of the medium 2, which is equal to HT, which are given by the equations 9 and 10. Now we have to determine how much amount of power is reflected into the medium 1 and how much amount of power is refracted into the medium 2. So that means we have to determine the reflection coefficient and transmission coefficient. So for that, now let us consider from the equation 1, 2 and 3 and from the equation 9, that is HT plus HI plus HI plus HR equal to HT, right? So I am writing that expression in terms of electric field components, where HI is nothing but equal to EI by eta 1 and HR will be equal to minus EI by eta 1 is equal to ET. HT is equal to ET by eta 2. Now I am going to simplify this expression to obtain the reflection coefficient, where the reflection coefficient is defined as ratio of reflected wave to that of incident wave, that is ER by EI. So on simplifying this expression, I get ER by EI is equal to eta 2 minus eta 1 by eta 2 plus eta 1. So this is the amount of reflected wave from the incident wave, which is denoted by gamma. Reflection coefficient is denoted by gamma. Okay, this is the amount, this is the value of reflection coefficient. And to calculate the transmission coefficient, let me consider this expression ET is equal to EI plus ER. So transmission coefficient, as I told you, it is defined as ET by, that is transmitted wave by incident wave, which is given as ET by EI is equal to 1 plus ER by EI. That is, I have taken EI common here, where ET by EI is equal to 1 plus, now substitute the value of reflection coefficient. ER by EI is nothing but it's a value of reflection coefficient. You substitute this value and you get ET by EI is equal to 2 eta 2 by eta 2 plus eta 1, where this ratio is denoted by tau, which is known as transmission coefficient. So we have obtained the values of reflection coefficient and transmission coefficient at dielectric media interface. Here we assume that media is a lossy medium, right? Suppose if I consider both the medias are perfect dielectric medium. Perfect dielectric medium in sense the conductivity of medium 1 and medium 2 is 0. And the permeability of two known dielectric do not differ appreciably from that free space. That is, mu1 will be equal to mu2 will be equal to mu0. This is free space permeability. In such case, the reflection coefficient becomes, where eta 2 can be written as root of mu2 by epsilon 2, where mu2 is substituted by mu0, and eta 1 is written as eta 1 is equal to root of mu 1 by epsilon 1, where mu 1 is equal to mu 0. If you substitute for those values, you get the expression in terms of permittivity of medium 1 and medium 2. And similarly, the transmission coefficient we are going to obtain in terms of the permittivity of medium 1 and medium 2, if the two dielectric medium are perfect dielectric. So now you have to note few points here. Both the reflection coefficient and transmission coefficient are dimensionless and may be complex. And the relationship between the reflection coefficient and transmission coefficient is given as 1 plus gamma is equal to tau. The range of the reflection coefficient lies between 0 and 1. So this is all about the reflection by a plane wave from dielectric media interface. In next session, we are going to discuss about reflection by a perfect conductor. Thank you.